All right, are we ready to get this show on the road? Okay, perfect. Let's do it. Let's do it. So thanks so much for coming. Some familiar faces here. Great to see you in the room. I'm glad I'm not the first session after lunch. You already were able to digest a little bit, and so but really excited to have you here. My name is Rene. I'm a product manager on the confidential computing team at Google Cloud, and today's interesting topic, right? How do we leverage the core capability of confidential computing with memory encryption, hardware isolation, but take it even further to enable this multi-party collaboration, especially when talking about the super sensitive data, that PHI, MEL models, PII, and things like that, that were either impractical, if not impossible, before. And of course, it's not about sensitive data in the future. Like Nellie Porter mentioned during the panel, the confidential computing is for all data. It doesn't have to be sensitive, but step by step. And then just like Raluca mentioned at the opening keynote, it's, confidential computing is not a silver bullet, obviously, right? Unfortunately, in cybersecurity, there are no silver bullets, and confidential computing isn't one either. There are other technologies, privacy-enhancing techniques like homomorphic encryption, MPC algorithms, but we discussed their limitations in the opening keynote already. And then other techniques like differential privacy, various anonymization techniques with their limitations as well. But let's get started. Let's start with the foundation, right? So let's talk about something super simple. We have a data owner on the left. We have a data consumer on the right. And this data consumer wants to leverage some insights from the data owner's data. OK, what other roles can be part of this kind of collaboration, this scenario? Well, we need some code to perform the processing itself. So we add the code author here at the bottom in the green. And then we need the environment to perform the processing. So we add the operator or the processing owner there at the top in red. OK, that's easy enough. So what are their motivations? Well, what are the motivations of all these different players? And they vary quite a bit, right? The data owner obviously cares about the privacy and security of their data, while the data consumer cares about getting those insights as easily as possible. Code author probably cares about giving some guarantees, some guarantees about what their code actually does, what is that processing. And then the processing owner cares about setting up that environment, setting up of that specific processing environment, so ease of deployment as well as cost, of course, right? They are the ones paying for that compute. OK, so ta-da, enter confidential computing. At first, it doesn't seem like much has changed, right? If I go back, forward, go back, and forward. So now you start seeing a few changes, hopefully. First, that processing environment in the middle is no longer just any processing environment. It's now a safe or a trusted execution environment, or a TEE. But even more importantly is that remote attestation, that attestation arrow that goes from the TEE to the data owner, providing verifiable guarantees that this box in the middle is indeed a safe, and more importantly, that the code running in that safe is the code that the data owner expects and trusts. So, but how does the data owner knows what code to trust, and what does that code do? Well, hopefully the code author provided reference measurements, reference values to the data owner, and the data owner audited the code, reproduced it on their side. Okay, so we've established the foundation for all the different roles taking part in this, as well as their motivations. Now let's take a look at three different scenarios of secure collaboration. Starting with something very simple, right? Again, we have our data owner on the left and our data consumer on the right. And, but here you may notice that their motivations have aligned quite well. The data consumer cares about the insights, hence they should probably be responsible for setting up the processing environment and, more importantly, paying for it, for paying for all that expensive compute. And at the same time, data owner controls when can their data be accessed, under which conditions, where, and through code authorship, they control what type of processing can be allowed. Bless you. And what can be an example of something like this in real world? Well, imagine the data owner is a healthcare institution, a hospital with all that super sensitive PHI. And the data consumer could be some research institution, a pharma or biotech, and they're trying to develop drugs, improve disease detection, and something like that. Okay, so that's the first scenario. Let's look at the second scenario, ML model protection, right? No presentation is allowed now without mentioning AI, ML, or LLM. So this is my mention today. And you know, everyone is very excited about this market, right? Billions of dollars at stake. And some of these models take tens of millions, if not hundreds of millions of dollars to develop and train. So obviously, these companies that develop the models really want to make sure those models are well protected. But imagine we have a startup or a company that developed one of those cool and very expensive models, and they now want to share that model with their customers. But obviously, they want to retain their IP, their intellectual property. On the other hand, we have customers that want to consume that model, but they may not be willing to share their data with that model due to privacy regulation. So, and this flexible architecture does allow for this, where data owner becomes also a processor as well as a data consumer, and hence they pay for that ML inference. They control their data while they're still being able to use that model that an organization on the left provides. And the code author, the model owner, they retain control over their model. What is a real-world example of something like this? Well, imagine there's a startup and they develop some cool model, some image detection model, for example, and they would love to provide that model to some companies. And on the right, we have, say, a social media company that wants to leverage that model in their app, for example. And but they're not willing to share access to their users' data due to privacy reasons for that startup who developed the model. So again, this setup would allow for this kind of win-win-win or win-win-win-win. You do the math. So, but yeah, that would be possible. Okay, moving on to the third and the last scenario. This is kind of more traditional multi-party collaboration scenario where all parties or multiple parties contribute their data to the processing, to the joint processing, and mutually benefiting from that processing that they contribute to. And this can be competitors. We heard some examples here in banking, right? It could be multiple banks sharing their customer data to detect fraudulent activity. It can be insurance companies, telcos, retail, or ad techs for that matter. And here, this is often called the data clean room example, or in our case, this is confidential computing enabled data clean room. So what else is interesting here? Well, obviously, we have 2 collaborators here only, but it can be 22 collaborators, right? There's no limit on the number of collaborators for such a scenario. And then finally, you can see that our collaborators don't have to be the data, the code authors or the processing owners themselves, right? They can outsource that to organizations that specialize in those activities without relinquishing any control over their data and their data privacy. Okay, so we described 3 different scenarios. Is there a system that can support these and many more scenarios? We believe so, and that's what we call at Google Cloud confidential space. So this is Google Cloud's trusted execution environment, or TEE. We build it on top of a very robust confidential VM offering we've had on the market for a number of years already. And as we leverage AMD's hardware for this, it supports complete lift and shift. So literally no code modifications are required to enable that. And most of our customers don't notice any performance impact when they run processing in confidential environment. We also believe in open standards. So this solution is built on top of open standards and using open source code. A little bit more details here about how we build this solution. But most importantly for us was usability. Usability was front and center. It should be super easy for our customers to adopt confidential space. So we provide out-of-the-box attestation verify service. Of course, customers can use their own as well. We, as I mentioned, leverage confidential VMs. But on top of that, we also took container-optimized OS, already a very secure OS, and further hardened it by removing things like SSA, serial, and many other things. And we did that in order to remove the operator from the trust boundary. And then we support your regular containers to run on top of that hardened image. We also seamlessly integrate with GCP's IAM, and that allows customers to ACL any cloud resource, your KMS key, GCS storage bucket, BigQuery, etc. And then we provide customers with very simple interface to define their policies, to control the conditions under which they're willing to allow the processing to happen on their data. So for us, it was all about providing usability, using an open standards, and having a very, very seamless and simple deployment for our customers. So hopefully I gave you a little bit of an insight of how we leverage confidential computing and extend it beyond kind of its core capabilities of memory encryption and CSP isolation, and unlocking this sensitive data for processing across teams, across organizations and boundaries. So yeah, thank you so much for coming, and please reach out. There's some links to our materials. We have tons of code labs and documentation about confidential space, and feel free to reach out to me directly as well.